Welcome to the Structural Engineering Podcast. This episode is organized differently than usual. We're talking with Connor Lewer about embodied carbon in the construction industry. And although I'm extremely interested in this subject, I haven't had the opportunity to really dive in and learn how to apply the principles here. Zach, on the other hand, has done some work in this realm and has the real questions on the subject. So while we usually both do some research and organize our questions, on this episode, I start us off with a true intro to embodied carbon curiosities, and Zach takes over about halfway to ask the serious questions. So whether you know a lot about embodied carbon in construction and how to reduce it, or you're just getting started, this episode is for you. And as usual, if you have any questions, send them in, and we'll get them to Connor to help you out.
Connor Lewer. I work for PEC as a structural engineer. I'm out here located in Fort Collins, Colorado.
Nice. Well, thank you for joining us. And we're talking about embodied carbon. Is that right on this episode here?
Yep.
And well, what's your, do you have training in embodied carbon? Like, how did you come to appreciate, understand a lot of this? We both, I assume, went to school for structural engineering, and I came out of that with structural engineering skills, but I have no guess on embodied carbon right now. So where did you get those skills?
I'd say it really started when we joined SC 2050 as a company. That was kind of our initial driver to start learning more and more about embodied carbon and what motivated us to do it a little bit more. So once we committed to that SC 2050 challenge and started taking steps to educate ourselves and our company first on how we can do better and really just get the baseline for what is embodied carbon and how can we make an impact on the industry and start cutting down and making a better future with green materials and the building industry.
Oh, man, that's wonderful. And since you said embodied carbon, I want to start with a very loose definitions here because I'm really starting from scratch. I've heard embodied carbon. I'm familiar with what the term means, but let's look at some definitions here. So embodied carbon, I think of it loosely as the number of resources we use to complete a project. It's like the budget, same budget we have on every project. But from a sustainability approach, what is the more technical definition used in the field? Like, what is embodied carbon?
So embodied carbon is really the upfront carbon footprint of a material. And so it really is involving the raw material extraction, the fabrication, and the transportation of that material. And then there's also embodied carbon within the construction and assembly of the material on site. And then at the end of life of a material, if that material is decomposing in a landfill after the demolition, or if it's reutilized as a new material or recycled. So all of that comes into what we call embodied carbon. But really what we focus on in design is mostly on that upfront cradle to gate is what we call it, which is the, again, raw material extraction and fabrication up until it leaves the fabrication plant.
And is that the bulk of embodied carbon is getting the building started? Basically, the operational is much lower?
Correct. And that's why one of the best things you can do with embodied carbon is use an existing building. So renovation projects and things like that are going to be really great on the embodied carbon front.
Okay, and just another very loose definition here, but I've heard embodied carbon equivalent. So this is just the impact, the environmental impact of material, relating it to carbon so we can add those up under the same roof, basically.
Exactly. Yeah. When we're talking about all the different greenhouse gases, we're trying to take a summation of all those different gases and bring it onto a level that's understandable and comparable between materials. And we do that with that carbon dioxide equivalent. For example, methane gas is a 25 times higher global warming potential than carbon dioxide. So that's accounted for within that carbon dioxide equivalent.
Okay. And just from my curiosity here, is that equivalent, the metric is basically global warming potential. Does methane be increased 25% to get to the equivalent embodied carbon? Is it kind of a literal to global warming potential?
Correct. Yeah, that's what we're really looking at is the impact that we're having on the environment with the global warming potential.
Interesting. So I've heard that buildings and the construction industry in general are some of the worst players in the embodied carbon game. How good can we be? There's a ton of transportation and machine time required for every single thing we do. Picture of what the goal is. What is our potential reductions? What could we be equivalent to? How do you look at this?
Well, with SC 2050 and the industry, what we're moving towards as a goal, hopefully, is zero embodied carbon by 2050. That's a challenge. So you mentioned buildings and construction being such a big player in the global carbon emissions, and it's about 39% of carbon emissions globally. So I think it's really interesting that we're just now starting to have more of a focus on it, and it's something we need to have a focus on. Whereas a lot of the other industries, like transportation, for example, have been getting a lot of attention in the past few decades, and now we're really finally starting to attack this big chunk of the pie. So,
can you give me an idea, a scale of what numbers we're looking at for embodied carbon? And so, if we were to break this up into like construction types, concrete, PT, steel, wood, obviously, or I assume being the least, can we do like a per square foot just to give myself a metric here?
Yeah, I guess I don't have a per square foot available. It's always tough to make a comparison since you're going to have different grid layouts and things like that within a building. Materials have different efficiencies, but what you'll see is generally concrete being the highest impact on embodied carbon, and then masonry, and then steel being third, and then mass timber or just timber in general being really the best you can do as a material.
Okay. If you do a timber building well, are you looking at zero embodied carbon? Because there's obviously transportation and fabrication and whatnot, or is it just a very small number?
Actually, a lot of the time now, we still have embodied carbon within timber buildings. Mass timber in general, people, or even wood framed, people a lot of the time will assume, well, trees are sequestering carbon. They're having that positive impact on embodied carbon. But embodied carbon is still coming into play from the forestry practices and then the milling practices and again, transportation. So all those different factors add up and actually bring embodied carbon into wood products. So with that said, there's more sustainable practices that can be done within those different approaches with the transportation, fabrication, and forestry, where we can start cutting that number down again and hopefully get it to below net zero as a material.
Okay. What other steps can structural engineers take to get us down to like a zero embodied carbon if a lot of that is sort of transportation, or is really our role to get it to the lowest material value and then the rest is a different team?
It's a tough question. I'd say it depends on the material and the project. And like I said earlier, there's not a really great answer right now, but it's taking small steps with each of the materials to try to get there by 2050 and start moving the industry that way. With concrete, for example, you can start looking into using more supplementary cementitious materials that are going to help bring your overall carbon footprint for your concrete mix down by using less Portland cement. For steel, you can source steel locally or steel that was made with an electric arc furnace versus a more traditional basic oxygen furnace. And then timber, again, if possible, sourcing that timber locally can help a lot. So a lot of those different factors are little baby steps that we can start doing within design and, again, work towards that goal of net zero in the next few decades.
This is sort of a silly-ish question here, but let's say, I want to make a good embodied carbon decision at work today. What would you recommend as just the baseline, beyond doing good structural engineering with embodied carbon in mind? So best bang for the buck, make a decision. Is this, my footings are a little bit bigger than they need to be? Connections are more complicated. Like, what would you tell someone that wants to be a little bit better within reason of their normal practices?
Yeah, definitely the easiest thing that we can do as an industry is within the concrete mix, specifying a more sustainable mix. And a lot of the times adding fly ash, for example, as a supplementary cementitious material might end up making your mix even cheaper, depending on the availability and the batch plant. But a lot of the time, fly ash within your mix will lead to a cheaper mix. So that's something where you can have impact on sustainability, but also the cost on the project. Beyond just that, you mentioned just efficiency in design, and that's something we're really pushing for a lot within the whole industry, is just pulling structural engineers on board as early as possible on projects. With a lot of the architects we work with, we're trying to be more involved in that early conceptual phase so that we can get a building that's laid out efficiently structurally. And that allows us to use the materials to their best efficiency with grid layouts and column locations so that those materials are being used most effectively and using less volume of material overall.
Okay, interesting. I do want to ask quickly about the concrete mixes that you're saying, we could put in fly ash. Is there a resource that has mix combinations that you can rely on? Basically, if you're interested in trying some fly ash, and up to 20%, I think, is a reasonable number. Is there a SE 2050 style resource that you can pull from to give you some evidence to submit that to a contractor?
Yeah, definitely. There's a lot of research that's out there. SE 2050 does have some good resources on their website for some recommendations for concrete mixes and some example specifications you can look at for working within your company's general notes and revising those. But in general, really the best resource that you could have for that is just your local batch plant and local concrete subs. Having those conversations with them, it really plays well in a design build environment. But even without design build, just making a few calls to some of your local batch plants and seeing what's available for their mixes. What have they been doing when asked about sustainability? How have they heard of these mixes performing on site and finishing? They're the ones making the mixes and finishing the mixes. So talking to them and having those conversations with them to see what works well in that area is really the best approach.
Hey, I've got another sort of general one for you, but what do you see in common building design that has the most negative impact on a better embodied carbon value? And I know you have already mentioned concrete, so I think it'd be completely fair to say foundations are often over-designed or larger than they need to be. But what could you pull out as most likely the worst thing structural engineers are doing in the embodied carbon realm?
Well, I'll say beyond just concrete in general, it's that efficient grid layout. So, and not so much on the fault of just engineers in general, but the whole project team. We need to have that upfront coordination to have an efficient structural system so that we can use the materials as effectively as possible.
Okay. So I've seen some numbers, and please correct this if it's wrong, but I've seen that concrete and steel account for about 11% of global greenhouse gas emissions. I'm curious, knowing that these materials take a lot of energy to produce and manufacture, do we know how good we can be? We've already talked about net zero being the goal, but let's say there's no technology improvements and it's just a practice improvement. How low can we reasonably get that number?
Oh man, that's a really good question. I don't know.
I was thinking about this as I'm done recording now, but I was thinking about this as I was writing these questions. Obviously there's some technology improvements and general practice things that need to be done. But like, if we could, what is the best we could do tomorrow? If we got every engineer to do like the best embodied carbon style design, like how good could we do without any technology improvements?
Pretty hard number to quantify.
Yeah, I know.
I'd say, maybe not for a tomorrow sort of conversation, but the bike clean bill, federal, been passed in a few states now. Currently, it's just requiring that EPDs, which are environmental product declarations, which outline the embodied carbon within a material. Right now, the bike clean bill is just requiring that those EPDs are submitted for materials on projects. Over the next few years, the bike clean bill is going to be ramping that up and setting certain requirements for materials that will get more and more stringent over time, and that will allow the industry to sort of adapt to that and meet that. And this is just for materials on federally funded projects, but with the amount of federal work going on, I think that's really going to start driving the industry to make these changes. We're seeing it already in, concrete plants are pushing more for sustainability. They know that it's a tough material for embodied carbon, so they're definitely making a move towards it. In steel, Nucor just came out with net zero steel.
Wow.
They're achieving that with using electric arc furnaces with a very clean energy grid and using a lot of recycled material that goes into that steel, a lot of scrap metal. So the industry is definitely starting to move that way, and we're starting to see more products available that meet those sustainability goals. But I think it's still those baby steps to get there over time.
Let's say that you have a client that's in a similar position as me, which is they want to do what they can, but they don't really know where the best place to start is. Maybe, let's say I need a 20,000 square foot office, and you want it to have the lowest reasonable embodied carbon, but how do you approach that discussion? So if, I came to you with this project, how do you start with the client?
That's where I think SE 2050 is doing a lot of really good things right now. They're starting with the industry with structural engineers and trying to get structural engineers up to speed with what's going on in the embodied carbon side of things. And that way we can have those conversations with clients and start educating clients and the industry as a whole on, what we can do better and how we can start taking those steps. So in that example, I'd say, yeah, the structural engineer should be the one having those conversations and being ready to talk about more effective concrete mixes or that better grid layout, effective use of materials and things like that.
So, I know it's not fair to give the numbers per square foot exactly, but I'm wondering sort of in your head as you're running through calcs, would you say generally that a concrete material is X times worse than a wood material? Is there a set of numbers that we can just start with? And, I know that it's a construction base or how you're using materials, grid layout, like there's many other details, but just from a total looking back at the whole picture, we say, concrete is probably better than steel.
Yeah. I guess for a rough comparison, on one project where we ran an embodied carbon report on, we found that this mass timber 2-story building was a little over 3 times lower embodied carbon compared to if it were a concrete framed building. So as a rough comparison with that example that still utilized a lot of concrete on that project, it was still 3 times more efficient. So
okay. That's wonderful. So I'm wondering about embodied carbon values of material. Is who releases the environmental product declaration? Is this a private company that puts that out and then it's a public good in some cases? Or is there a sort of government agency that releases EPDs on a product? Does anyone check it? Or does, someone just make up this steel beams 1 carbon?
So yeah, it's really similar to an ICC or ESR report where it's on the fabricator to provide that, but they're hiring a third party to come in and provide that analysis and give them that EPD data. And so it's really a tool to allow them to sell their material better. Otherwise, they could be pushed out of the market, and where a contractor or design team might go with another material provider who has an EPD available. So it's similar in that sense.
So I've heard some confusion, much of it my own, on carbon negative, carbon neutral, and any other positive connotation carbon term for a structure. Using trees as the reference point, can we get to a carbon negative position with a product that soaks up carbon while growing and stores it for a long-term solution, but we still need to construct the building and use many other materials, man-hours, occupy it? And this is a very similar question to how good can we be?
I think we're a ways away from being able to achieve that currently. I mentioned net zero steel earlier. There's masonry blocks that are being researched right now in Boulder that have organic materials that sequester carbon throughout their life. So there's a lot of research being done to achieve net zero or net negative with carbon in a material, but it would have to get pretty far into that negative once you factor in, like you said, the construction and all the labor involved with assembling materials on site. There's that aspect of it as well. So I think it's definitely achievable by that 2050 goal, but it's going to take a lot of research, a lot of smart people, and just motivation in the industry as a whole to keep moving there.
Okay, well, that's it for my intro questions. Zach, take us to the next level.
So Connor, dive us into concrete a little bit. Where does the embodied carbon come from?
Well, when you look at a concrete mix, concrete's made up of 3 main ingredients: cement, aggregates, and water. And when you look at that by a volume or mass basis, the overwhelming majority of that mix is in the aggregates. The aggregates account for roughly 80% of the mix on a volume or mass basis. But when you look at it from an embodied carbon perspective, the embodied carbon within concrete, 90% of that is attributed to the cement within the mix. So we really want to focus in on the cement.
So what is it in Portland cement that is so bad?
Well, it's really coming from the raw material extraction, and then in addition to that, the calcification process that is the chemical reaction that concrete undergoes during the production of cement. So between those two is what attributes to cement having such a big embodied carbon footprint.
And that makes it seems like it makes it a huge challenge because those are two pretty important things. When looking at cement, you brought up earlier being able to replace it. Walk us through some of those techniques that you're using.
Yeah, definitely. So I mentioned that Portland lime cement is a raw extracted material, and it's produced for the sole purpose of being utilized within a concrete mix. We can utilize supplementary cementitious materials, or SCMs, within a mix that are actually byproducts that are produced from other manufacturing products, and utilize those within concrete mixes to bring down that global warming potential, since we're not producing those materials for the sole purpose of being utilized within concrete.
So tell us where those materials come from. Which ones are you using mostly?
Well, with the industry, we're really using three mainly within concrete mixes: slag cement, fly ash, and silica fume. Slag cement is a byproduct of steel production. Fly ash is a byproduct of coal burning power plants, and silica fume is a byproduct of silica metal production. So depending on your region, these can be some really great options to utilize within your mix. And again, they're just supplementary materials, so they're replacing a portion of that Portland lime cement, not truly the full mix of that cement.
So that makes a lot of sense. I think is probably really helpful for most of our listeners on how can they instantly kind of start adjusting the embodied carbon, changing the mix and stuff. What else can you do to be more efficient with concrete in the sense of design?
Yeah, with design, there's a lot of different options. Precast is going to be a really great option. Precast allows you to eliminate a lot of the temporary formwork and labor involved with doing cast in place concrete. Beyond that, within precast, there's hollow core slabs, which have cylindrical voids pushed through the length of the member. What that does is keeps the thickness of the material where you need it most and allows you to eliminate a lot of volume of material while still retaining a lot of the strength and deflection capacity of that member. So you're, again, using those materials efficiently and getting the best use out of them. Another option that's done a little more commonly in Europe, but it's starting to become more popular in the United States, is bubble deck. Bubble deck are these plastic spheres that are cast within a concrete slab. And those are just essentially spheres of air once the concrete is cast, that again are reducing that volume of material and keeping that thickness of material where you need it. So that concept of introducing voids is going to become a really big factor within sustainable design.
So I'm kind of thinking about cementitious materials. My next thought goes to masonry. What things can we do with masonry? We understand you can change the mix a little bit, but how does masonry help when it comes to embodied carbon?
Yeah, well, within the mix within masonry, we talked about SCMs, the supplementary cementitious materials with concrete. Those are going to be even a bigger factor within masonry. Masonry requires less than half of the compressive strength that is usually utilized within cast in place concrete. And because of that, we're able to utilize a much higher percentage of supplementary cementitious materials. We've seen mixes of up to 80% Portland lime cement replacement be used successfully. Beyond that, too, masonry intrinsically has voids. I brought up that concept of introducing voids and utilizing those voids and doing partially grouted walls instead of fully grouted walls when it makes sense on a project can help reduce that volume of material and save on the embodied carbon and then a little bit on cost by doing that as well.
So I think just moving along with our building materials, kind of steel is the next one that jumps out at me. How does steel have embodied carbon?
Well, most of the embodied carbon within steel comes from the steel milling process. And then there's a good bit on the fabrication side as well. So when we're looking at a steel mill, a lot of the embodied carbon is within the blast furnace. More traditional basic oxygen furnace is the coal-powered furnace that you're used to seeing in pictures with the smoke billowing out of it. These furnaces are only able to utilize around 70% of recycled scrap metal that comes into the mix. And then the rest of that is raw extracted material. Newer technology is the electric arc furnace, and about 2/3 to 3/4 of steel mills in the United States have converted to electric arc furnaces now. And essentially what they do is run off of the electrical grid. So even on a dirtier grid, we've seen electric arc furnaces be about half the embodied carbon compared to steel produced in a basic oxygen furnace. So one of the best things you can do with steel is source steel that was produced in an electric arc furnace.
So to kind of a similar point to concrete, what can we do when it comes to the actual design opportunities for steel?
Yeah. Like I mentioned, most of the U.S. has converted to electric arc furnaces. So being able to source local steel is going to be one of the best options. Um, Local steel is not only going to be a better chance that you'll get an electric arc furnace producing that steel, but then also you're saving a lot on the transportation. The two biggest importers of steel into the U.S. are China and Russia. And so when we're talking about bringing in steel from outside of the US, you're now factoring in shipping that steel halfway across the globe as well.
So what about using different shapes, or what techniques are you personally using on your projects to just mitigate the amount of materials when it comes to steel?
Yes, steel joists are a really great option. Steel joists compared to a wide flange beam have about half the weight for the same span and loading condition typically. That's not to say exactly half of the embodied carbon, because there's a little bit of embodied carbon that comes in with the fabrication that's involved within a steel joist with assembling those joists. But again, that concept of introducing voids is going to be a big factor on lowering the embodied carbon on that front. That's not to say that it's great for every application, though. For a roof application, steel joists are really great. And we've done them for composite steel joists for like second floor, for example. But a lot of the time, steel joists could have vibration concerns. So making sure you're weighing all the different factors that go into that design choice to make the right selection for that project. Again, using materials efficiently. Another option that is, again, more common in some other countries, but gaining some more popularity in the US is castellated steel beams. Castellated beams start with a wide flange beam, and they make cuts along the web of the beam, lift the top section up and slide it over and weld it back down. This increases the depth of that beam while using the same amount of material, again, by introducing those voids. That allows you to get more effective strength and deflection capacity out of that member for the same amount of material. They also look really great and allow you to run some mechanical ductwork and fire sprinklers through them as well.
So I'm thinking through building materials. The last one I'm really thinking about is wood. So where does the embodied carbon come from wood? We talked about that wood sequesters carbon dioxide, but how do we get to having a positive number?
Yeah, so wood starts with that negative number with an embodied carbon, which is from that sequestered carbon. But through the forestry of the acquisition of that lumber, and then the milling process, and then the transportation, all those different factors bring in that embodied carbon into a wood product. So when we're talking about a wood having that embodied carbon value, unfortunately, it does typically bring that value up to a positive embodied carbon number once again.
So before we jumped on, you were telling us a pretty interesting story about wood mills. Would you mind sharing that again?
Yeah, this was super interesting. Wood mills actually run about half of their energy is biofuel. That biofuel comes from around 12% of the material that's brought into the wood mill is waste material and not able to be used as an architectural or structural wood product. So they burn that and use that to produce energy. And a lot of the time you might think, well, burning wood emits CO2, carbon dioxide, into the environment. That doesn't sound very sustainable. And yes, it doesn't sound like it, but the EPA recently came out stating that biofuel is net zero, because that carbon dioxide that's emitted by that burning of the wood is offset by that volume of wood growing in a tree. So as long as sustainable forestry practices are happening, and thankfully in the US and Canada, where most of our wood comes from, we have very sustainable forestry practices. As long as that's taking place, it's seen as net zero. The other side to this too is if wood decomposes in a landfill, which again, this 12% of material is waste material, it would end up in a landfill otherwise. If that material is in a landfill, it would decompose, and wood, when it decomposes, emits methane gas, which I mentioned earlier has a 25 times higher global warming potential compared to carbon dioxide. So it's also preventing that process from happening.
Yeah, that's pretty fascinating. I would have never thought about that. So when we're thinking about different types of lumber that we get to use as structural engineers, my mind comes to, a solid sawn shape or glulam, or maybe flat plate materials like OSB and plywood. How do those kind of work when it comes to embodied carbon? Is one better than the other? Should we be looking at just trying to focus on just utilizing one, or do they each kind of have their place?
Well, there's a really great analogy that I heard with wood products in general when it comes to embodied carbon. And it's like comparing a cheeseburger from a fast food restaurant to a salad that you grew in your own garden and made at home. That salad's usually seen as more healthy compared to that fast food cheeseburger. It's the same with the wood products. When you have more processing that goes into that product, it has a higher embodied carbon. So the more fabrication and assembly, as well as adhesives that are required to make a product, lead to higher embodied carbon. So due to that, softwood is going to be about half the embodied carbon compared to glue-lams or LVLs. And then OSB is going to be about double the embodied carbon compared to plywood. So when you're able to, specifying plywood over OSB or solid sawn softwood lumber compared to a glue-lam or LVL member, it's going to help a lot on the embodied carbon front. That's not to say that softwood, solid sawn lumber is always the answer. Glue-lams and LVLs definitely do have their place when you need longer spans or tighter deflection criteria.
So is there any other techniques as structural engineers that we can do or help the architect, the design team with?
Yeah, definitely. Utilizing trusses is a really great and already popular approach with wood products. Trusses will allow you to accomplish spans that might not be possible otherwise with wood as a material. And beyond just that, with a lot of stick frame projects, if you do a lot of multifamily, for example, you could look at spacing your studs at 24 inches on center instead of 16 inches on center, and maybe aligning your roof joist with your studs. That might eliminate the need for a double top chord. So some of those different approaches can help a lot on the embodied carbon front and take little steps to help cut down on the amount of material used on a project.
That's a really good description of all the different materials, and talking about, the product and kind of how you brought up the embodied carbon portion from extracting the raw materials to the construction site. You also kind of mentioned the end of life. Is there anything else you can tell us about the end of life of a material when it comes with respect of embodied carbon, and what techniques there might be that people are looking at utilizing?
Yeah, definitely. I think, unfortunately, the industry hasn't had a lot of focus on this end of life side of it yet. We're really focused on that upfront side right now, with this being such a new push in the structural industry as a whole. At the end of life, it can be a material going to a landfill and decomposing, or it could be recycling and reuse of the material. With steel or wood products, it definitely is a pretty common thing now for that member to be reutilized in a project. Steel in general is very highly recyclable. I think around 97% of structural steel is recycled. So steel as a material is really great on that front.
Now you talked a lot about embodied carbon. We also, at the beginning, you mentioned a little bit about operational carbon. As structural engineers, is there anything that we can do to help benefit the built environment when it comes to an operational standpoint?
Yeah, definitely. I'd say one of the biggest things we can do is thermal bridging and effective detailing in that sense. Thermal bridging is something that is missed on a lot of projects that we've seen. And whenever you have steel, as an example, penetrating through your exterior wall for, say, an exterior canopy or maybe a screen wall on the roof, a lot of those penetrations through that building envelope can bring in a lot of heat into the building as that thermal barrier. So a lot of the time that's not even accounted for on the mechanical side. So that could cause their mechanical systems to run at a rate higher than what they had anticipated potentially, and increase that operational side. So effective detailing when it comes to thermal bridging can help a lot on that operational side, while sacrificing a little bit with more material on that upfront embodied carbon side.
So if there is to be any architects listening to our podcast today, or maybe some structural engineers that would like to help influence architects to be better at embodied carbon, what other techniques are there that we can share?
Insulation and finished materials are really going to be one of the best things that you can take a look at on the architectural side for embodied carbon. With insulation, it's a little tricky because it's, again, that balancing act between operational carbon and embodied carbon. maybe it makes sense to utilize a thicker insulation material that has more embodied carbon to have a better performance on the operational side. There is also products out there, such as plant-based materials or some foaming agents, some of these newer insulations that have net zero or a reduced embodied carbon compared to a more traditional insulation product. So utilizing some of those and finding out what's available in your area can have a really big impact on a project.
Now, I think that's a lot of what Max and I wanted to talk to you about. What things have we not brought up that you think would be interesting to discuss with or have our listeners hear?
Mentioned briefly earlier, but one of the biggest things you can do on the embodied carbon standpoint is existing buildings. The most efficient use of a material is something that's already constructed. So whenever you're able to do a renovation project, so if any owners listening or have an older building, maybe taking care of that building and reutilizing it as a new space can have a really big impact instead of using a lot of new raw extracted material and the construction process involved with that.
Considering I know the least about embodied carbon in this room here, can you give me some pointers on where I could go learn a little bit? So, I would love to reduce embodied carbon. I am really behind this idea, but as I've proven, I don't know anything. Does SE 2050 have some good educational resources that I can lean into, or is there another source that might be better?
Yeah, absolutely. Right on their website, they have a database full of a lot of resources for different materials and easy approaches to start taking those baby steps to reduce embodied carbon on a project. They also have resources to find out how to join SE 2050 and how to get more involved with the movement. And they also have a list of all of the different firms that have committed to SE 2050. So if you're an engineer at a firm who is not yet a part of SE 2050, definitely take a look at that list. And if you have any friends or connections within the industry that are in firms that are committed, they would definitely be willing to help you get that started within your firm. I think that's something that's super exciting within embodied carbon and sustainability within structures is it's really a industry movement where it's a lot of sharing of knowledge and resources between firms. It's less competitive than a lot of other things we're used to seeing within the industry.
That's great. And sort of in the same ballpark, and truly my last question here, but is there a good resource that I can use to account for the embodied carbon that I have in a project? Like you had mentioned, maybe joist might be better than a solid sawn member. Is there a resource available that I can take some of this information from and maybe value my own projects with a certain number of embodied carbon and then compare that to the next project and say I reduced the embodied carbon by this amount per square footage? Basically, how can I build these calcs?
So we've looked at a lot of the different Revit plugins, and we've had difficulty using them effectively on our projects. So our approach that we've been doing is just within Revit, creating schedules that do volume takeoffs for all the different materials within our project and using data that's available on SE 2050. They have an LCA tool where you can plug in the volume of material, and that will give you the embodied carbon for that material. So that's our approach, and I think that's a really good starting point. But like I mentioned, there is a lot of different Revit tools out there. So,
well, Connor, thank you so much for joining Max and I today. I think we both learned a lot of information about embodied carbon, and we know our listeners will as well.
Yeah, thanks for having me. This was a lot of fun.